This will be a introductory seminar on two-way post-tension slab designs, which is going to be the natural progression from what you have learned in one-way slabs and post-tension beams. They're very similar topics with some slight modifications, but everything that you have learned so far is basically going to transfer right into two-way slab analysis and design. So very quickly, two-way slabs are used in pretty much every type of structure. At least in North America or United States, long span beams and one-way slabs are typically used for parking, whereas two-way slabs can be used from parking, hotels, office, podiums, buildings, apartments, storage, whatever you have. A two-way slab is usually been used and successfully been used. In general, the columns are typically in a 2-to-1 ratio between sides. Obviously, a 1-to-1 ratio would be ideal. Ideal rarely happens, but if you're in less than the 2-to-1, typically the flat plate is the economical choice. The large difference between a one-way slab and beams is the fact that there's no longer any beams or walls to provide continuous support. So everything is going in two directions to columns that support the slab. As I've just mentioned, the slab is designed to resist the load in both directions, north, south, east, west. So instead of designing a one-way slab north-south and beams east-west, you're obviously just replacing the beams with the other direction of the slab. One-way slab systems obviously are strong in their one direction and then weak in the other. And so in the weak direction, or the perpendicular to strength, you design for temperature and shrinkage, which is usually 100 psi of pre-compression or 0018 of rebar. Two-way slabs do not have a quote-unquote weak direction. They are structurally designed in both directions, so the one-way temperature and shrinkage reinforcement does not apply to these systems. The other major difference is the columns are relatively small. Since you don't have a relatively deep beam that's going to crank in a large moment, the columns are typically designed for axial load. Now, obviously, there is some moment transfer. You're going to have unbalanced moment for punching shear and other things, but it's the axial load that is the primary design component for these columns. The other difference is shear design. The VCI, VCW, VCN equations do not come into play for two-way slabs. It's controlled by punching shear. And so those equations are going to be different because obviously it's a different methodology or different mechanism. In general, similar to beams and at least one-way slabs, these are best used to resist uniform type loading, parking obviously, hotels, offices, stuff like that. We usually design for something of pounds per square foot of superimposed dead and live load. If you're resisting a very large post load or a transfer slab with 75, 80 kip point load, those are typically tough to do with two-way slabs just because of the parabolic profile we use and the limited depth system. So when you're doing uniform loading, two-way slabs are great. If you have a whole series of just large point loads, typically that's challenging, and beams are usually the right solution for those type of situations. This is a very simplistic difference between the one and two-way systems. Up top is the one-way system where the slab is designed in the one-way, the short direction. This would be the weak direction where you have temperature and shrinkage, and a beam or a wall provides bearing support in the east-west direction where the slab is going north to south. So the major difference for a two-way system, which is shown here, is you're designing the slab north-south and then also east-west. So the load that is right here in the circle will travel hopefully up to the midspan here, then go right and go left to the column in the same way it travels this way, and then it goes up and it goes down. So you're designing for 100% of the load in both directions to carry it to the column, which is obviously the main vertical support of the system. So in general, two-way slabs are relatively thin structures. For most general applications, again, garage, office, podium, stuff like that, you're between 7 to 12 inches thick. That's a typical range. Now, if you start getting to, mat foundations or, very, very, very large transfer conditions, pools, landscaping, it might go larger, but for the most part, 7 to 12 covers a large majority of structures. The slab thickness, as usual, is based on the longest typical span, either direction. So again, if you have a 1-to-1 ratio, it's very economical. Obviously, if it's 2-to-1, it's going to be economical in one direction and then a little bit over in the other. But again, typically the largest span in either direction is going to dictate the slab thickness, assuming all loads are being equal. The balance loads, the equivalent loads, the percentage we design for, 65 to 100%, is still very critical. So the information or the philosophy that we use for one-way slabs and beams is still applicable to two-way systems. The stress checks are similar, but they appear more restrictive compared to the one-way slab and beam systems. The major difference is when you design a one-way slab, you're designing a 1-foot strip of concrete. That may be 200 feet wide. Lots can happen in a 1-foot wide strip. And so you're allowed some forgiveness, and they let you go to 12 square root. Whereas the two-way slabs, you're designing an entire panel width. So that may be 30 feet wide. And whatever happens in that 30-foot width is going to amortize over to encompass the whole design strip. And so even though the stress checks appear more restrictive, they're actually more similar than they look, and I'll get into that in a little bit. The flexural design is effectively the same. The code minimum rebar is a little different, but for the most part, the FPS equation, the Whitney stress block, all that kind of stuff is exactly the same. The only major difference is you are having a different equation for the minimum rebar the code requires you to have. In the direction of design, obviously, the two-way slabs require 125 psi pre-compression minimum. That is a restrictive value. You can't argue your way out of it or use some fancy mathematics. It does not include any type of restraint or loss of pre-compression. It's simply a way to judge how much PT should be the minimum value. So, if your building has no shear walls because there's no lateral system, because you have no wind or seismic, or you're completely subterranean and have walls all over the place, 125 minimum is just the number of strands regardless of restraint. Having said that, anything you use structurally needs to be 125. So if you have beams, caps, drop panels, thickened sections for some reason, if it's required for strength, it's 125 minimum. Now, having said that, if your design is exactly 125, you're probably over-designed in terms of thickness. Generally, most slabs we design are in the 175 to 200 psi range, and that's where I would typically shoot as a general rule of thumb. But again, there is a code minimum. Conversely, there is no maximum pre-compression value, which is a debatable topic. From a numerical standpoint, you can just add more and more P over A, more strands, more pre-compression to make the stresses work. So if I say a 200 psi slab is a in the quote-unquote good design range, what is a 400 psi or 600 psi slab? In my opinion, overbalancing and then also adding a lot of pre-compression are numerical solutions when your slab is too thin or your beam is not deep enough. So make sure you don't really go crazy with the pre-compression. Again, there is a minimum value of 125, but no maximum. So as the engineer, you have to be cognizant of not just overloading the system with strands. If you are more used to rebar systems, the column strip and middle strip philosophy does not apply. There is no 75%, 25%, 60-40, that kind of stuff. You have a 30-foot width or a 20-foot width. Everything's the same. You put PT in it, rebar in it. There's no, percentages that go across the structure. This is a typical view of a parking structure. Hopefully you can see the columns right here. Relatively small, considering that it could be holding up 5 or 6 stories of concrete. Not a whole lot of moment transfer. Again, primarily axial load. You can see here, this is roughly about a 29-foot span in this direction, and that's roughly probably about 28 feet in that direction. So the slab thickness is based upon, obviously the greater of the two, but they're basically the same value. A note, at the top of the columns, at these floor levels, we do not have caps or drop panels. We are using stud rails for punching shear resistance. I'm a big fan of a big fan of stud rails to resist punching shear, excuse me. And for relatively light loads with parking, hotel, apartment, office, stud rails are great. When you start getting into the more larger loaded structures, we typically go for a cap, which you can see right here at all these columns. Same general column size, again for axial load only, or sorry, for primarily axial load with some minimal moment. But the cap right there is used for punching shear, but also it's used for flexural stress, because obviously your section modules S goes up, your A goes up, and your D for your rebar design obviously increases with the cap. So while a lot of people would assume that the cap is there primarily for punching, which it does help with, there's also a lot of benefits for flexural, which I'll get into later on. This photograph is obviously the end view of a two-way flat slab that I think was one of the first ones I'd ever done. This photograph is fairly old, but since it's the first one, it's one of my favorites. One of the things I like about this photograph, and this goes into one of the previous slides where I said the slabs are relatively thin. If you look at this slide, we have banded tendons right here, which I'll cover in a little bit, column right here obviously, and then there's a span of roughly 30 feet, and that's an 8-inch deck. That right there is a great picture of why we use post-tensioning, why we do stress checks and strength checks and all the different things that make it a little more complicated than other materials. Nobody can touch us in terms of thickness of material. If you were to take a rebar only deck to go this 30 feet, it'd be at least 10 or 11 inches thick, typically 2 or 3 inches thick, or 2 or 3 inches thicker than the PT equivalent. So right there, if you go from a 10-inch slab from an 8-inch slab, that's a 25% increase, which is, a lot. If you were to make this a steel structure going 30 feet, most likely you'd have an 18 by 35 minimum girder. You have a 6-inch floor of concrete and metal deck. Right there is 2 feet. We're at 8 inches. We beat it by a factor of 3. We win the thickness of material contest, hands down. Nobody can touch us. One of the things that I've seen engineers get in trouble with or start getting into very, let's say, interesting designs is trying to make the slab even thinner than it should be. We win in the size of material. No one can beat us. Don't try to be the extra hero. Do the slab thickness correctly, live with that slab thickness. No one can touch us, but don't try to go down the rabbit hole of take another 2 inches off and then you're in the 500 psi compression range, you're 220% over balance and make stresses work. We win the slab, no reason to do anything more than what we're already doing. This is a residential structure that was done a few years ago back east by a friend of ours. And you can see here, two-way flat plate slab. The nice thing about this photograph is that there's an undulating slab edge, which again, for hotels, for apartments, you're gonna have balconies and stuff like that. Nothing you can't do with PT or not do with a flat plate. Obviously, these are cantilevers over here and cantilevers on that side. You design accordingly. But the other thing about this photograph to look at is you can see, again, relatively tall structure. Let's say this is 10 stories, relatively thin columns, relatively thin slab, and we're using stud rails for the punching shear strength. So again, you're having no cap, no beams. That keeps the floor heights down. Shoring costs, reform, stuff like that, but this can make the building shorter than it would be in different materials. If you're in a high seismic zone, that decreases the overturning moment and the vertical distribution. So again, we are the shortest, thinnest structure out there. Aside from removing PT and rebar, this is where we shine. But again, use the right slab thickness. Don't try to be an ultra hero. We're heroes enough as it is. So there is a historical progress of where we got to the point we are today and then where we're moving forward. So quickly, I'm going to do a back in the day, this is how we did things and how we got to this point now. So when people started using two-way flat plate slabs, they were originally constructed with a uniform strands, in both directions, very similar to a rebar system. So basically, let's say you had 2 strands every 2 feet, that would be all over the place. If you are used to a rebar system, and you obviously have seen those before, you have top and bottom rebar all over the place, and you can literally walk from one side of the slab to the other without touching the forms because there's so much rebar that you never actually have to touch the form supporting the concrete. And that's kind of what the PT systems looks like. You just had a mountain of reinforcement that was interweaving between each other in multiple directions and multiple elevations, which is what we call a basket weave approach. The column strip, middle strip philosophy was used. So again, it was very similar to rebar, just now instead of rebar, it was post-tensioning. It worked great. The problem was it was very challenging to construct. Trying to interweave, interlock, whatever word you'd like to use, all these strands in different directions, construction joints, all that kind of stuff was very challenging to build. And when things are challenging to build, it takes longer, they're more expensive, and nobody wants that. So the performance was great, but there had to be a way to make this more economical, or people just weren't going to do it. And this is a photograph from one of those back in the day, obviously the sepia tone to indicate the passage of time, but hopefully you can see just the column strip here, a whole bunch of PT, the column strip here, a whole bunch of PT, less in the middle strip portions. And as it comes down to the support right here, all these things want to be in the same zone. So you have a lot of post-tensioning, then obviously some rebar, which is going to be tough to see, intermingling each other. And trying to get this stuff threaded to be everything at the right location to the best of your abilities, again, was extremely challenging. And challenging is not something you really want in a general construction practice for your material. Now, if you look at a rebar-only two-way slab, you can see it's very similar to what we saw before. You can see the formwork over here, but there is so much reinforcement in multiple directions that you can walk right across it and never hit the formwork. The other thing about rebar slabs that I've always struggled with, even years and years while doing them, is trying to figure out the load path. I know it's a tight view, but if you're standing right here, how does my body weight get to this column? Does it use those bars? They take it this way and it comes that way? Does it go this way and comes that way? What's the dominant reinforcement? What attracts the load? What's the load path? And in rebar two-way slabs, it's a lot more just we're going to catch the concrete, very simplistic point of view, and put all this rebar in each direction to hold it up. And don't get me wrong, they work fine, but there's just a lot of rebar in these systems. So based upon the challenge to construct it, the people in the industry back in the day decided we're going to revise our construction methods to make this more economical, and they came up with the banded uniform design philosophy. Basically, there's no difference in analysis. This was not a let's use finite elements or equivalent frame. This was how do we build this more efficiently so we can keep designing it. It almost had nothing to do with the engineering, had everything to do with the construction. The solution was in one direction, we'll call it the band direction. You're going to take all the tendons in your design strip, let's say 30 feet, and instead of having them at 2 feet on center, you're going to compress them into roughly a 4 or 5 foot wide pseudo beam that would go column to column to column and basically be very similar to a girder line in steel. So you would say along grid D, I want 20 strands. They would put typically 4 bundles of 5 strands right through the column core, and that is your girder line. In the perpendicular direction, it's more similar to a uniform space tendons or a one-way slab. So in the band direction, you're going to have a 4 foot wide chunk of 20 strands. Nothing in between grid D and grid C, which are 30 feet apart. In the perpendicular or uniform direction, the tendons are going to be similar to one-way slab in that they're 2 or 3 feet on center, and they're going to go over the bands like a 14 by 22 framing into a 21 by girder, and then the 21 by girder takes it right to the columns. The other difference between the two is that while in the band direction we call out a specific number of tendons, 15, 20 strands, in the uniform direction we typically call out about a kips per foot. So the supplier can either do 1 strand at 18 inches on center, 2 strands at 36, whatever works best for their system and for economy of construction and speed. There's a maximum tendon spacing of 8 times the slab thickness. And that's usually not an issue in terms of exceeding it. But again, instead of saying we want 127 strands, equally spaced from grid 1 to grid 10, we'll tell the suppliers we want 20 kips a foot from grid 1 to grid 10. How you get us 20 kips a foot in a generally equally spaced pattern is up your discretion. The analysis method is the same for both directions. It doesn't have a special finite elements for the bands and equivalent frame for the uniforms or vice versa. You can do everything exactly the same way you like to do it. You can design the bands and the uniforms exactly the same way if somehow you wanted to flip the bands at a later date. Basically, they're exact same analysis. This is purely a construction thing so that you're not doing a basket weave. You're basically doing a girder line, and then you put in the beams, and that's your floor system. They tested it. It worked great. It's been used for decades, millions upon millions upon millions of square feet. Great system, easy to build, easy to see how it works, and it's a great way to do things. This is a close-up photograph of the banded tendons. Hopefully you can see there is a group of 5, 5, and 5 here, typically about 9 to 12 inches between the groups. There is a column right here. I apologize, it's kind of hard to see, but there is a column right there. We have stud rails for punching shear reinforcement. But this is the banded tendons. It goes high over the supports where the moment is tension on top. Then it drops back down, creates the balance load effect, matches the moment, and comes back up. But notice there's a column right here too, and a column right here. All the tendons basically go right through the column core. The other thing that's great about this construction sequence is note in the vast majority of the span, the tendons of the bands are low, where the strands of the uniforms are high over the support. Basically, the column line is a support, and all the strands are high over the column line. So there is a multiple inch gap between the uniform strands and the bands. So once they put the bands in, they put the uniform strands over the top. There's no interlacing. There's no basket weave. This goes extremely fast. And also from a load path point of view, if you're standing right there in the deck, it's easy to see that part of your weight goes to this band, part of your weight goes to this, drops it off to the bands, and then the bands take it there and there. Now, obviously, that's a simplistic point of view, but in relation to a rebar system where you just have all this rebar all over the place and the load path is somewhat subjective, this, from an ultimate strength perspective, that holds up the weight, drops it to the band here, drops it to the band there, and then these bands or girder lines take to the columns, and that's your load path. It's easy to see how it works, and you as the engineer are directing the load path of the system rather than the concrete, quote-unquote, catching it once the slabs are unshored. This is another photograph that indicates the uniform strands. You can see here we have uniform direction strands going left to right on the screen. And there are 2 strands per bundle. Hopefully you can see the 2 strands there and there. Let's say roughly 2 feet on center, or 30 feet or 30 inches on center. They go right across the structure, continuous reinforcement, again, high over the supports because that's where the tension on top moment is. Low at mid-span, tension on bottom. That drape creates our equivalent or balanced loads. And again, any kind of loading that's right here is taken by these strands, dropped off to this band, and the band goes right to the column. Again, the load path is clear. Now, the one interesting thing about this photograph, if you're more used to beam and one-way slabs, if this was a beam and this was a beam, you would have temperature and shrinkage reinforcement in the quote-unquote weak direction, which you don't see. The temperature and shrinkage does not apply to post-tension concrete. Now, some engineers don't like it, which again is fine, and so they will put a triangular mat of rebar as the pre-compression from the anchors, basically, as the pre-compression from the anchors basically goes into that zone and tries to give you the pre-compression of 100 psi. There's no code requirement for that. That is purely a owner's preference or engineer's preference. We don't do it. I've never once seen a problem with it. But again, if that's something you want to do, more power to you, but it's not required. This is another blow-up view of a band and uniform system. Hopefully, again, you can see the bands go right through the columns. So that's your direct load transfer. Punching shear obviously is a big deal. You can see there's some rebar here and rebar over the columns, which we will cover in a little bit. The uniform strands are anchored at mid-depth of slab, but they're above the bands, which again, minimal interaction, easy to construct. They come down, they come up over the supports, and again, no interaction, nothing, no mixing and matching. It's very similar or very simple to construct. The other thing is, in opposite of the rebar only photograph I showed you, there's lots of places to walk here, get your pants or boots dirty. Because of the effectiveness of post-tensioning, one of the main financial benefits of our systems is the reduction in rebar. With the current cost of things these days, concrete prices have gone up, PT has gone up, but nothing has gone up as much as installed rebar. So when you take out a whole bunch of rebar, you're taking out a whole bunch of costs, and the post-tensioning obviously is extremely effective. But it's a clean system, minimal reinforcement, lots of places to pour concrete, get good consolidation. Like I said before, you can walk the deck, look at all these strands. Very clean, very efficient system for the two-way slab layout. This is another example of a two-way system. Again, minimal rebar. You can see there's rebar at the top of this column support here. This is actually the jamb of a shear wall. You can see here there's a shear wall right there. Again, the same general profile. The banded tendons go right over the column or embedded column in the shear wall, then start draping down and go back to this particular column. Uniforms go over the top, no interaction, simplicity of construction. But note how there's almost no bottom rebar. We have a small amount of 4s at 30, but there's no top rebar anywhere in these zones. Basically, for most designs, you're going to see that you only have top rebar at the supports, or in this case, at the columns. Out in the middle of nowhere, there should be a very light mat of bottom rebar if that's what you choose, but no top rebar anywhere. The PT takes care of all of it. The rebar is usually just very centralized at the columns or end of wall supports. So where are we going with this? We're always trying to improve things. And one of the ways that they are trying to open up more markets for PT is to do something called the double banded design philosophy. And it's the same general profile in terms of analysis. There's no major difference, or you have to buy different software modules. Again, it's going into construction to achieve a certain goal. So they did some physical testing and analysis at Virginia Tech. This was, I think, 1 or 2 years ago. Reports are being written, reports have been written, codes are being revised so that you can do bands in both directions. That's the key. So instead of having bands and then uniforms perpendicular, you're going to have bands in both directions with effectively nothing besides some rebar in the midspan in both directions. So no uniformly spaced strands, no strands 2 feet on center. You're going to have 15 strands on grid D. You're going to have 15 strands on grid 3, and between grid 3 and 4, or C and D, no uniform strands whatsoever. It's just going to be rebar to a certain extent. Again, the analysis is exactly the same. The only difference is one direction. The tendons will all be a ½ inch lower. So technically speaking, there's a slight reduction in moment capacity. But again, you're talking about some percentage points, not factors of 2. So if you really want to be clever and design each direction for a loss of a ½ inch of depth, you can flip the bands in any direction, or however you want to do it. But again, there's a slight reduction in moment capacity, but again, nothing horrific. The reason we're going to do this, or the reason some engineers want to do that, is basically they want to create the potential for tenant improvements. So if you have an office building or a medical office building and you want to put in new equipment, but you don't want to x-ray the slab because you have to put in some quick bolts or epoxy bolts to anchor the machine down, if you know you have 20 feet by 20 feet in the middle of the structure of no PT, that's going to just make the tenant improvements easier. Conversely, if you want to add a stair, add an opening in the slab for some reason, again, if there's no PT, you're not going to break strands. One of the downsides, for lack of a better word for PT, is that it's a rubber band. It's continuous. When you snap it at one location, you lose it anchor to anchor. And those anchors could be 200 feet long. And so if you break something in grid 7, it has an impact from grid 1 to grid 14. And obviously there's, force being released is slightly dangerous, and people are nervous about doing that. So the intent was, let's minimize or minimize the location of random PT, keep it centralized over the columns, so that the owners of these buildings have a lot more freedom to do tenant improvements or different things they're building without doing a whole bunch of destructive testing. Again, the goal is to expand the market. There's some people that are, I should say, some owners that don't want to deal with PT. Again, if they have tenant improvements or different potential future options, they just don't want to have the headache, let's say, of locating the strands, re-anchoring them, re-stressing them, all that kind of stuff. And this is a response to those comments. So in the, moving into the future, what we're going to do is, if you can see the screen, hopefully, you're going to have 19 strands going north-south. You're going to have 15 strands going east-west in a general pattern. So no PT here, no PT here, no PT in the mid-span. So in theory, if you wanted to come in as the owner and just, chunk out this blue rectangle, you would be doing it with a fairly certain attitude that you're not going to run into post-tensioning. Yes, you're going to cut some rebar and, have those kind of issues, but in general, you're not going to break any strands because there's no strands in this zone. So the demolition, the, tenant improvement, stuff like that is going to improve, or has the potential of improving. The downside of this, or the complication of a double banded system, is effectively the columns have to be in line in both directions, effectively. I mean, they don't have to be perfectly, but within reason. In my neck of the woods, at least where I live and work, I rarely get columns to align in both directions. But if that's, your situation, you definitely have the option to do a double banded layout, and that does give you a lot of flexibility in future designs, primarily for getting rid of or not having to deal with broken strands or drilling through them. So going back to the way things are currently done, we're going to stick with the banded and uniform philosophy. Effectively, one of the questions we get a lot of is, how do you determine which is the band and what is the uniform direction? And there's really no set answer for that. It kind of depends on the geometry of the structure. I would say in general, the banded tendons are typically the ones where the columns are most in line. So if your columns are only aligned east-west, guess what? Your bands are going east-west. Conversely, if it's north-south, they're going north-south. Now, having said that, if the columns are aligned perfectly in each direction so that you could do east-west or north-south, we typically have the bands going in the long direction of the structure, simply because at each of the anchorage points for banded tendons, you have to add in additional reinforcement per the code. This is band anchorage reinforcement. It minimizes the potential for blowouts and helps amortize the load out to the slab. If you have, 8 column lines in the long direction, but 40 in the short direction, having the bands go in the long direction decreases the band anchorage reinforcement, which is a cost savings. But if that doesn't work for you, doesn't have to, that's purely an economy standpoint. You could easily do it in both directions. If you have a consistent cantilever, everything off grid, A has a 5-foot, 6-foot cantilever. We typically try to put the uniform tendons in that zone. This is not a code issue. There's nothing wrong with having bands go to the uniform, but just as a general concept, when you have a uniform loading as a cantilever, we'd like to match that with uniform space PT. So if that works out and we do have a consistent cantilever, we put the uniforms in that direction. One of the common misconceptions for two-way slabs is that bands cannot go into a pour strip. We put bands in pour strips all the time. We put them into construction joints. The concrete's not smart enough to know the difference. After about 4 or 5 feet from the anchorage zones, the force of the strands is going to amortize out. The concrete's not going to know the difference. So don't change your framing method because you're going to put a pour strip here or a pour strip there. Do the right framing method. Use your CJs or pour strips where you want to. Put those locations, design it correctly, and it'll be just fine. But don't reinvent the wheel because a band, in theory, it is a misconception that cannot go into pour ship. We've done it all the time, no problem whatsoever. This here is a typical photograph of a two-way flat plate. This is a podium structure that we did up in Northern California not too long ago. As you can see here, the columns are roughly aligned going left to right. Not perfectly, of course. You can see some curving of the strands going through here, but going in, let's say, the up direction, there's a column there, there is a column there. And if we were to run the bands this way, there's no column there. So just by default, the bands were chosen to go left to right simply because that is where they lined up the most. If all these things were perfectly aligned, you could do it either way. But again, because we have a band anchorage at each of these points, which would be, right there and right there, there's 1, 2, 3, 4, 5, let's call it. If we were to do it in the other direction, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're almost doubling the band anchorage reinforcement. That's the only reason, besides the geometry of the structure, that I would choose bands versus uniforms in certain directions. The other thing that's great about this photograph, I think, is highlights some of the beauty of PT that you don't get across with the numbers. If you look at this band right here, let's say we have 25 strands, they're continuous all the way across the structure. So all the load with continuous reinforcement, its ability to share the load, to redistribute between spans, you have a lot of potential in those segments because there's no lapping, it's active reinforcement, and it is one continuous rubber band across that structure. So you have a lot of potential there. Seismically, because you have continuous elements, those are great for chords, for collectors or drags, whatever you want to call them. There's no lapping, it's active reinforcement, and any load in these strands gets dragged all the way through the shear walls, through the diaphragm into those structures. So from a diaphragm perspective, the PT is continuous, which is always best for the reinforcement, regardless of dead plus live conditions, which obviously is the governing case. The continuity effect of PT benefits dead plus live, but also benefits for the seismic design and performance of these structures. So if you look at this particular photograph of a two-way slab, you can see here that there's a shear wall, column, these things perfectly align. In this direction, they also effectively perfectly align. So in these situations, you could have bands in either direction. It would make no difference whatsoever. And this happens every now and then. But for the most part, we deal with worlds that look like this, where the bands go left to right because that's where the columns align. If you go up and down, you can see the column starts here. There's another column right there. Then if you go upward, you're missing a column. And so that kind of defines where the bands are going to go. So regardless of the other things we've discussed or the cantilevers and stuff like that, this is basically telling you where the band or the girder line needs to be placed. And so a lot of times the decision is somewhat made for you just because of the geometry of the structure. So in the design analysis of two-way slabs, there's obviously some design steps that are very similar to other materials. So I'm going to go through these relatively quickly and just try to highlight the ones that are specific to post-tensioning and not just generic design steps. So obviously loading is critical, dead live, any specific loads. You need to lay out the columns and walls appropriately so you get the right design approach. I think probably the most important thing about PT design, aside from knowing what you're doing, is the slab thickness. With the software out there, there's lots of brands, a lot of great pieces of software out there. If you get the slab thickness right, you're going to have to try really hard to screw up. You can still do it, of course, but the slab thickness being the right thickness, plus or minus, is almost going to ensure a good design with the software that's out there. The biggest problems I've seen with engineers in terms of design of structures is when the slab is too thin. It should be 12 inches, but they want to be a superhero and make it 10 inches. To do that, you have to add in a lot more strands to increase the pre-compression, and that usually leads to overbalancing. And that usually leads to cracking, potentially some blowouts, and other things that are kind of more detailing issues. The right design is the right slab thickness, plus or minus 200 PSI. If your slab is 300-400 PSI, I'm going to say that your slab's way too thin. As I mentioned before, we win in slab thickness. There's no reason to go thinner. We win, leave it at that. The money is saved with a reduction in rebar, not so much taking an extra inch or two out of the slab thickness. Yes, there's a seismic benefit. Yes, there's a vertical load benefit, but the amount of rebar you're going to add for PT, or the amount of reinforcing you're going to add, and then coupled with the punching shear issues and just the construction issues, it's not worth it. So the question is going to be, of course, how do you get the right slab thickness? And this is how you do it. From the PTI manual, and this has been in a couple editions of the manual, when you're doing a slab thickness, the typical value is L/45, which you can see right here. And that's the base point for any slab with effectively minimal superimposed load. So parking, hotels, stuff like that, you're looking at, parking has effectively no superimposed dead load, 40 pounds a square foot live load. Hotels will be 40 pounds. Residential is about 40 pounds a square foot. You maybe throw in 10 or 15 for partitions and stuff like that, but very minimal loads. But L/45 is the good starting point. So for a 30-foot span, multiply 30 by 12, divide by 45, and that's 8 inches. So basically a 30-foot span holding up relatively light loads, 8 inches is the way to go. So what happens when you actually have more loading than just effectively nothing? My rule of thumb has always been a 1% or a 1 for 100 rule. Effectively, every inch of thickness of concrete is about 100 pounds a square foot. Now, depending on how comfortable you are, it may be 3/4 of an inch, or you really want to shave the penny. That's fine. But in general rule of thumb, 1 to 100 is where I start with. When you start going beyond 100 pounds a square foot to 300 pounds a square foot, we start looking into caps. But in general, start with extra 1 inch for every 100 pounds a square foot. So if you have a storage facility, or you're supporting, whatever it is that weighs 250 pounds a square foot of live load, let's say trucks, you're going to start with a 30-foot span at 8 inches, and then you're going to add 250 divided by 100, which is 2.5 inches. That'll get you a 10.5-inch slab. Now, as I mentioned before, typically anything more than 100, 125 pounds a square foot, I start looking at caps. One of the things I'm going to hammer home a few times, and this will hopefully save you if it comes to that, the cap thickness and its plan area has a very dramatic and has a very strong impact on the slab thickness. So if you design our budget a slab with caps, and let's say in this point it's 10.5 inches, and someone, the architect or someone in your firm says, we don't want caps, we're going to use stud rails for punching, that's fine. Punching is an issue. Obviously, caps, stud rails, you can use them. The caps will have an effect on the slab thickness. So if you get rid of them and use stud rails, reevaluate the slab. They are not interchangeable just like that. Now, in my experience, typically if you have a thicker slab supporting 300-400 pounds a square foot of load, like a podium structure, and you budget for a cap and take it out, I'm looking at typically about 2 more inches of thickness of concrete, so you don't end up with massive amounts of pre-compression or overbalancing. But again, my point of this discussion is, if you have a cap and you're happy with the slab thickness and you get rid of the cap, do not think it's an apples to apples comparison. When doing podium structures where you have a slab that is going to support typically a 4 to 5 story wood structure, I use effectively a 1-to-1 ratio, also using caps, and this is assuming minimal rough live load, the typical 20 pounds a square foot. Now, if you're in a high snow area, obviously adjust accordingly. If you have 75 pounds a square foot of snow, that's obviously a lot more than 20. But typically for each level of wood framing, I add 1 inch of thickness. So again, a 30-foot span, 4 levels of wood, I'm going to be using a 12-inch thick deck with caps. Again, keyword caps, do not interchange with stud rails until you re-eval the slab thickness. So again, this is the general way to get the slab thickness correct. Start with L/45. L/45 should be based upon the maximum typical slab thickness, and then adjust from there based upon your loading conditions. As I'm going to say one more time, caps and stud rails are not interchangeable, especially for higher superimposed loads. So once you get the slab thickness correct, obviously you want to design for stresses, and you have to design for the stress limits in the code. For Two-way flat plates, the tension stress is less than 6 squared F prime C. The compression is less than 0.45 F prime C as well. Now, in general, you should never have a compression quote-unquote failure or flag. That means something has gone seriously wrong. But the tension stress less than 6 square root, that's an interesting value because that's substantially less than the 7.5. And also in one-way slabs and beams, you're allowed to go to 12 square root F prime C in the stress design. So the question is always, why are two-way slabs punished? This is where that those values, come out of the code, chapter 24 of ACI, section 24.5.2.1. This gives you the 3 different values of stresses or classification of stresses. U being uncracked has to be less than 7.5. However, if you have a two-way slab design, which you can see down here, you're a class U structure, but it's not 7.5, it's 6. You're knocked down from 7.5 to 6 only if it's a two-way slab. And if you are a two-way slab, it has to be class U. There is no two-way slab class T. So basically, you have one limit, which is 6 square root, and that's your design value. So the question will always be, why are two-way slabs penalized? And as I mentioned before, when you design a one-way slab, you're effectively designing a 1 foot wide strip. And if that 1 foot wide strip goes, 7, 8 bays, lots of different things can happen in a 1 foot wide segment. And so you're allowed some forgiveness, and they let you go to 12 square root, so you're not constantly having all these different slab thicknesses or added rebar and stuff like that. Now, when you amortize the one-way design over, let's say, a building width of 200 feet, everything's going to, average out. But in that 1 foot segment, it gives you some forgiveness. Now, when you design a two-way slab, you're designing from the trib point of halfway to the left to the trib point of halfway to the right. There's a lot that can happen in 30 feet. You can have a large point load here, large point load there. Who knows what's going to happen. But because you have a singular point of support, this is where the stiffness comes from. This is where the max moment, max stiffness, the max stress is going to be generated. And as you go away from the column, you don't have the stiffness anymore. And so the distribution of moment is going to go down. So the stress across this entire trib width is not going to be one single value, but it's going to be a whole series of values as you're seeing here. So what the code has you do is you take this variable stress distribution, you design for an average design stress across the width. So the fact that you have a little bit more here and a little bit less here, it doesn't really matter. You're going to take that whole average across the system, and that's why it's 6 and not 12. So if you look at it, that this point right here was 12 square root, which is the T-zone of transition, and this is the 0 point, you can kind of see where they got the 6 square root from. So in a sense, they are allowing you to design for higher than 6, but because of the way the two-way slab is done and the fact that you're doing a 30-foot wide panel, not just a 1 foot strip, you get to average it out across that width. So it is more restrictive in a sense, but in the global sense, it should be roughly, about the same. This is where you get the compressive stress limits in the table before the tension stresses. You have the 0.45 here and the 0.6. And again, for all the years I have been doing this, I can't remember one time I had a compression failure or compression flag. If you get a compression issue and not tension, something has gone seriously wrong. But just in case, 0.45 and 0.6 F prime C are your limits. So once we have those established, you determine the band in uniform direction. You lay out your tendons. You start the slab designs. Cover to the PT and rebar will depend on the fire rating, your exposure to corrosive elements, stuff like that, owner preferences. Columns and walls are models. You obviously have the span lengths based upon the architecturals. You break out your designs for trib widths based upon the column loading in each analysis. We typically use parabolic profiles in two-way slabs because parabolic profiles work well to resist uniform loads, which typically is what we're supporting or resisting in two-way flat plates. Again, parking, hotels, apartments, stuff like that. You're always dealing with a 20 pounds a square foot dead, 50 pounds a square foot lighter live or something like that. You apply the loading, do the design, and then be accurate. Now, when I say be accurate, I'm not trying to be condescending or, tell you to pay attention, do your job correctly. Somehow you wouldn't be doing your job correctly in steel or be accurate with wood or something like that. As we've mentioned before in this class, and I know I have, and I'm sure Dirk has, one of the things that I think scares people, engineers, about PT is that, for lack of a better word, it will penalize you for being grossly conservative. The big difference between post-tensioning and rebar is PT is active reinforcement. It is there 365, 24/7. It never goes away, provided the strand is still there. That's why we do a stress check and an ultimate strength. In a lot of ways, the stress check is probably more important because the everyday condition occurs, as stated, every day. The ultimate strength, where you increase dead load by 20% and live load by 60%, may never occur, and hopefully it doesn't. Obviously, that's life safety, that's important, but the stress checks of what we do every day with active reinforcement are extremely important. So this is the example I like to give out. It's a Friday afternoon. You have to design these 5 segments, and you just got finished doing a steel building. So in your mind, this is a very small area. It's not going to change anything. You would design this 30-foot segment, excuse me, this 30-foot segment, 14 by 22 beam. You put the beam there, 14 by 22, 14 by 22, 14 by 22, put it there. 15, 17, 20, 25, 30 feet. If the 14 by 22 works for 30 feet, it's going to work for all those conditions. No one's going to ask you for calculations and all that kind of stuff. By default, we all get that. Again, it's passive reinforcement. It just means it'll never get used to its full capacity. There's no actual downside of putting in a stronger member than you need. It just never gets used. So you want to get out of there, you want to go see the latest movie, and you're going to say, okay, I'm going to design this 30-foot segment, and then I'm going to use that CGS of 1 3/4 inches at all these different locations, because if I use the steel or passive mentality, I know that's going to work. The problem you get into is this is active reinforcement. And so, as we've talked about numerous times, the equivalent load is determined by 8 multiplied by F. A is the drape dimension from the support to midspan, and this is the L squared term. The L squared is the span, and that's what actually hurts you the most. So let's assume F and A, F and A are the same. So the force is always the same, or the number of strands. A is constant because we're going to use 1 3/4 for all 5 conditions. So with the L of 15 feet, we get a value of 0.036. With an L of 30 feet, we get a value of 0.00. Note there's a whole different zero involved. So now we're talking a big difference, not just a little bit here and there. So if you take those 2 equations and divide them, if you have 100% of load in the 30-foot span, that will create a balance load effect of 400% in the 15-foot span. That is going to crack the slab. That is going to create cambers. That is possibly going to create blowouts. That is not the right solution. Even though the strength, if you're to cut a free body diagram and you have all those tendons at the bottom, from a strength perspective, it's great. You have extra strength. The problem is when you're lifting that thing up every day of its life, you can't be 400% higher than the weight of that slab. That's where cracking happens. That's where blowouts happens. You have to be diligent because, again, the force in the strands is always present. It's just not going to be there for life safety applications. Now, having said that, I don't mean to design slabs for every foot they change L. Typically, I'm 3 or 4 feet, 5 feet on center. But if you go back to my previous slide, there's a cascade effect because I want to match the weight of concrete that those tendons are affecting. And so I don't create bad situations by just being grossly conservative. Design PT, the least amount of PT possible, design it accurately. And if you're concerned, if you're nervous, you want to be conservative, which I do all the time, do it with rebar. Rebar doesn't create cracking. I've never seen rebar create a blowout, and it's great for crack control. And if it's never used, it's always there. There's no downside to it. You're accurate with PT, you conservative with rebar. And this is a localized blowout from a condition like we just discussed. The tendons here, you can see there's about 25 of them. They were draped too low. One of the fascinating things about post-tensioning is, at least in my point of view, once the tendons are stressed and nothing quote unquote bad happens, I stop even thinking about the job. The tendons are the strongest when they're stressed, and then they start relaxing and drop their force. The concrete is at its weakest, and then each hour, day, month, the concrete grows stronger. So the tendons get weaker, let's say, the concrete gets stronger. So if it holds at stressing, most likely 99.9% of the time it's going to be fine moving forward. But the great thing is about PT, you don't have to wait to see if it's going to work. Once you stress it, if it has a problem or there's an overbalance condition, we can see here, it's going to let you know about it. If you look at these chunks of concrete here and over there, those are not just flecks or little shavings of concrete. I mean, those are big chunks of concrete that just got completely lifted up out of the system. So again, you want to be accurate with the PT, and then obviously this applies to construction as well. You want to install it correctly, but be accurate with the post-tensioning. 125 pre-compression minimum, that includes caps, beams, thickened areas, whatever you're using structurally. If for some reason the architect just creates a thicker section that is architecturally needed, the 125 really doesn't apply. Obviously, add some rebar, but the 125 minimum is meant to be just the base number of strands that we don't want you to go below. There's nothing really magical about it. It could have been 130, it could have been 120, but 125 is the number. As I mentioned before, it's prescriptive. It's thou shall be greater than 125. I would also say that if your design is 125 and it's working, your slab's probably too thin. Again, we're more in the 175-200 range, so I typically don't deal with the 125 value that often. And if you are dealing with it, you might want to look at your slab thickness because you may be a little bigger than you need to be. In two-way slabs, we specify the number of tendons for the band direction. We don't call out a force per se. We usually just say grid D, we want 15 strands. Now, we might put a force on there just so it conforms to the calcs, but for the most part, we want 15 strands or 20 strands. We don't give them a force and then say you figure out the number of strands. The number of strands, as you know, is the APS value. So we, as the engineer, have to know that. So in that direction in the bands, we tell them we want X number of strands. Obviously, we check balance loads, the same 65 to 100% in a one-way or beam system is what we use. Once you have the tendons, the force you like, adjust the drape to get the balance loads correct. Then you're going to check allowable stresses, assuming that all works and no adjustment is required. You're done with the PT design. The next step is just checking rebar, which is ultimate strength. There are code minimums. And then we check the Whitney stress block and make sure we're good. If we're not good, we add rebar where required. For typical designs, in my opinion, the code minimum top rebar over the columns will govern the vast majority of the systems. If you're designing a slab where 90% of the columns need more rebar than the code minimum, I'm going to guess that your slab's too thin. So that's another thing to keep you out of trouble, hopefully. Once you've designed for allowable stresses, the ultimate strength should only involve rebar at this point. Whenever you change the number of strands, the force, or the drape, that affects the stresses. So you have to go back to the previous stress design and do that. So again, once the stresses are satisfied, PT is done. Now we're just checking rebar. From a shear perspective, punching shear is the controlling shear function. Stud rails, caps as needed. As I mentioned previously, adding caps has a direct impact on the pre-compression value because your A section cross-sectional area will increase with a cap. You're also increasing your S, your section modulus, so your M over S stresses go down. So again, there's a benefit fluctually in terms of strength and also for stresses. You want to verify the deflections are within acceptable limits. If you have the right slab thickness, you have good balance loads, your rebar is covered by code minimums, your deflection should be laughably small. If you're used to dealing with steel and L over 360, I'm typically L over 2000 or something like that. Typically, if you do a good job with the PT design, the deflection should be relatively laughably small compared to other materials. Again, verify that for yourself, but if you're having large deflections, you should also be having strength or stress issues. So to quickly go through how we're going to design PT slabs, We're going to do a very quick example. I'm not going to go through all the numerics because that's beyond this primer course, but we're going to go 3 spans. Span 1 from here to here, span 2, and then span 3. Quickly, the process of designing this configuration. So I'm going to focus on just the input from PT data because that's what I use. It should be the same for whatever software you choose to use. We have span 1, span 2, and span 3, which you can see here at 13 feet 9 inches, 29 feet, and roughly 16 feet. We have a 28.17 or 28-foot 2 trib, and because we're at 29 feet and 28.5 feet plus or minus, we're going to go with an 8-inch slab as our slab thickness based upon the L/45 ratio. We're going to do a parking, so we're going to have relatively light loads of 30 pounds a square, 3 pounds a square foot of dead load, 40 pounds a square foot of live load, and then we're going to do the drape. Now, as I mentioned before, we typically use parabolic drapes. So 1, 2, or 3 are what we choose for most two-way slabs. For the spans, number 9 and number 8 are for the cantilevers. We don't have a cantilever, so we're going to focus on 1, 2, and 3. 1 right here, you can see it as a simple parabola from the support center line to the support center line. That is only used for academic purposes. That's not how they build things in the real world. So typically we're using 2 or 3 flat over the column, or 3 is a little bit of reverse curvature. For simplicity, we're going to use number 2 in these situations. So we're going to assume the tenon is flat over the extent of the column, then basically you have a simple parabola and then flat again. Probably, to be technically as most accurate as you want to be, 3 is probably similar to how it's built. We typically use 2 for two-way slabs because they're relatively thin, but either one of those would work well for your purposes. So when you start the analysis, PT data will give you an initial design, and typically the initial design does 2 things. 1, it will maximize or design it to be over 125 while at the same time satisfying stresses. So if you look at this output, I am exactly at 125, which is fine. Typically I want to be higher just because you don't want to be kissing the minimums. But more importantly, for this discussion, you can see here every one of our balance loads is less than 65%. And we typically like to have a 65% minimum. The other issue with this, or other aspect of this particular initial design, is the fact that the stresses are all working. The 6 square root of F prime C of 5,000 is 0.42 or 424 psi. The worst case we are is right there, 305. So we're still about 100 psi less. So we satisfy stresses and then some, but our balance loads are a little on the low side. So regardless of the stresses, I am going to then adjust the strands. So instead of using 12, I'm going to use our 12 kips a foot. Now I'm going to be at 16 kips a foot, which you can see right here. I adjusted the drapes. I have 93, 76, and 93, which are obviously all between 65% and 100. My P over A is 167, which is obviously a lot higher than 125, but not getting crazy high. And then subsequently, my stresses are all way less than 0.424. The highest stress we have is 0.158 here. So you could make the argument that maybe our 8-inch slab maybe could be 7.5-inch slab in these situations. But again, before you just say, oh, I satisfy stresses, my design is good, check P over A, and then make sure your balance loads are in the right percentage. A couple extra strands is not going to break the job. You're going to get better performance, limited deflections, and in my opinion, that's the right answer where you should go with that. The one thing you have to be very careful of in balance loads is that if you go back to the previous slide, we had 4.5 inches here and 4.5 inches here, and we had a 93% balance load. You change relatively short spans by very short numbers. This is a 1/2 inch. I mean, a 1/2 inch is hard to see with the naked eye. It goes from 93% balance load to 160. While that's not horrifically high, it's still high. The point in this discussion is typically on your shorter spans, this was about 16 feet, I think this was about 14 feet. I typically go a lot closer to the 70% range than higher range, because again, if the field, kicks the chair or adds the wrong chair, and this goes up by half of an inch or even a quarter inch, all of a sudden you're overbalanced. So typically that balance load, highest you can get in the longer span, which is here is the 29 foot, and they can be a little bit lower in the shorter spans because obviously you don't need it as much. And if there's any kind of, not lack of perfection in the field, you can have a lot higher balance loads than you want to. But again, balance loads in the right range, P over A in the right range, and stresses should come out nicely. The thing about balance loads is there really is no stress check for balance loads. If you have 400% over balance, you're typically not going to get a flag that says, this is not a good idea. We're 161%, which is obviously a lot higher than 100. But if you note here, if you just look solely at stresses, there's no code violation. So again, there's no code section for balance loads, but it typically is a very, very good indicator of a design that is going to, work well and minimize the chances for overbalancing and blowouts. So this is the final product. Obviously, as the engineer, you want to make sure the calculations that you have match the drawing. So the CGS is 4 and 4, 1 1/4, 1 1/4, and so forth. And this is the general profile of the strands and cross sections. And again, if you draw the moment diagram to the tension side, it's going to be tension on the bottom, tension on top, tension on the bottom, tension on top, and then back to zero effectively. So again, this profile should match the general profile of the moment diagram, and that should, roughly be what you're designing for. Now, from an ultimate strength perspective, these are the strands up here, and then you can see the top rebar, 5 number 6s, same and the same. Now, obviously, this column has a lot more moment than this column here, a lot more axial load, yet they have the exact same amount of rebar, 5 number 6s. That's where the code minimums kick in, which we'll cover in a little bit. So again, in my opinion, a very good design is in the 200 PSI range, good balance loads, and where the ultimate strength is governed by code minimums in the majority of conditions. So also, if you can note here, the relative length of these bars, 2.75 feet, 2.75 feet. Those are relatively small. Typically in our details, we usually go about 5 feet past the columns just for development, bar cutoff, and stuff like that. But again, these are all generated by the code minimums and not directly for flexural strength. So getting into flexural strength, the same thing with one-way slabs or beams. We have 1.2 dead load, 1.6 live, and 1.0 times the secondary effects. The secondary effects are something we have covered quite a bit. It's the same philosophy, the same mentality, whether it's a beam, a one-way slab, or a secondary or a two-way slab. You have the drape of the post tensioning in an indeterminate structure is going to create some, moments or some shears, some reactions that creates moments. You would have to account for that. I realize, again, we're beating a dead horse, but secondary moments will increase the moment demand at certain locations and decrease it at others. So ignoring it is not conservative, and also it's statically incorrect. So we don't want to do that. We've all seen this photograph for the beams or the slabs. You have rebar, you have post tensioning, you have tension from steel, tension from PT, the compression of the Whitney stress block, and this is your standard equation. The only difference is the d sub p value is a constantly changing value because the drape of the strands are constantly changing. So your capacity is literally different every foot of a slab section because the PT is no longer in the same location. That's a major difference between rebar, where rebar is always in the same location, whether you're at the face of the column or at mid-span. Top rebar, bottom rebar, those don't drape, they stay consistent. The FPS equation, again, is exactly the same between beams and slabs. There's nothing, no different equations here. These are all exactly the same. Everything is based on the L to D ratio, length divided by the slab thickness in our case. So less than 35, use this one. Greater than 35, use that equation. Same as before. So if we examine our 3-span condition for the L over D ratio, you'll see something kind of interesting. So for span 1, it's 13.75 feet with an 8-inch deck. You do the mathematics, that's 21. So therefore, you're going to use equation number 1 on the previous slide. For the bigger span of 29 feet, you do the mathematics, and that comes out to 43.5. That means you use equation 2. So literally on spans 1 and 3, you're going to use FPS 1, let's call it. On span 2, you're going to use FPS 2. So when span 1 and span 2 meet up at the center line of the interior column, you're going to have literally 2 different FPS values depending on what nanometer you are on the center line of the column. So in theory, I shouldn't say in theory, but in practice with the numbers, when you have a different FPS value on the interior side of the first interior column or the exterior side of the first interior column, you're going to technically have numerically different moment capacities. So if you do see that, and a lot of times in the output you'll have, let's say, 15 strands, and then on one side, the longer side of the FPS equation, the equation 2, it may need 4 number 4 bars. On the other side, it may only need 2 number 4 bars for the exact same column the exact same slab over the column. It doesn't mean anything's really changing in the real sense. It's just the FPS equation is being flip-flopped. There's a slight difference in the FPS values, so therefore you need rebar to compensate. That's just the way the equations work, so if you see it, don't think you've done anything incorrectly. For the positive moment regions, or mid-span tension on the bottom, if your stress is less than 2 square F prime C, which for 5,000 PSI concrete is 141, you need 0 bottom rebar anywhere. We typically don't do this. We typically always have a bottom mat of rebar for crack controls, for diaphragm, stuff like that. I know engineers in the East Coast will go for this type of design, so they have no bottom rebar anywhere. I've seen it a few times when I've been back east. It just looks odd to me, but they've been using it, works fine. It's just a design preference. The second you go above 2 square F prime C, then you have to put in some rebar. So it's 142, not 141, you're putting in some rebar. The equation for that rebar is N sub C divided by 0.5 Fy, which is 30 KSI for most of our conditions. N sub C is the tension stress in concrete at service load. So again, even though we're talking about rebar, which is typically ultimate strength, we're going to go back to the service load condition. So what's going to happen is we're going to look at a service case, determine the triangular area of tension, figure out that force, which is going to be something in kips, divide that by 30 KSI. That's going to be the amount of rebar we're going to use in the bottom. Obviously, you check that against ultimate strength. The largest one governs. But right here, again, to stress a point, no pun intended, this rebar is purely for service conditions. The ultimate strength is in addition to this. Now, over the columns, regardless of what stress you have to put in this rebar. There is no way around it. You can be all in compression. You can have no tension anywhere. You're going to put this rebar in. Ask the question, why am I putting that rebar in if I have no tension? The short answer is this is effectively meant for punching shear, to activate the tension strut of the punching shear resistance. I'll cover this in a little bit, but punching shear is our Achilles heel, and these two-way flat plates, like shear is for anything else in concrete. Fluctually, I think we have unbelievable amounts of reserve strength, catenary action, spider webbing, whatever you want to call it. But punching shear is immediate. It's not really ductile, and once it starts sliding down, that's pretty much it. So when you determine this equation, 00075 multiplied by ACF, ACF is the gross cross-section in both directions of that span. So even if you're designing in north-south direction, you're going to take the east-west ACF and the north-south ACF. Whichever one is larger, that's the governing value. Because again, you're designing for punching, and punching is a global thing, rather than just in the analysis, or just not in the direction of design. So in terms of punching shear, this is the equation that we would use. You have the axial load effect, and then there's the unbalanced moment. There's nothing magical about these values compared to reinforced concrete. The only major difference is going to be the equation. Since we're post-tensioners, we have to make it slightly different. Instead of it just being 4 square root, we have beta sub p multiplied by the F prime C of concrete. You get to use 30% of the pre-compression force from your strand. So technically speaking, more pre-compression does increase shear capacity. I wouldn't actually recommend doing that, but from a numerical sense, it does. B sub O is the same as before, D is the same as before, and the V sub P term I'll talk about in a little bit. So again, same mechanics, same everything, but of course we have to use a slightly different equation. The B sub O is the perimeter of the critical section. The A sub S or alpha sub S dimension is 40, 30, and 20, just like it is for rebar concrete. The B sub P value cannot be greater than 3.5. Apparently, you just can't use 4 in post-tension concrete. The one caveat that we're trying to change, but right now we haven't, is the F prime C value, the square root of that number, cannot exceed 70 psi. Basically means you can't go more than 5,000 psi concrete. Now, having said that, you can use 6, 7, 8,000 psi concrete in your slab designs. It will benefit you fluctually in stresses and strength in terms of flexure, but you're not going to get anything out of it for punching. Why? I don't understand it. We've tried to change it because you can use 6, 7,000 psi in rebar concrete. What engineers have done is when they're using higher strength concrete past 5,000, they a lot of times we could just go back to the regular non-PT equations for shear to benefit from that. But having said that, we are trying to change it. But if you're doing a design and you go from 4,000, it doesn't work, you go to 5,000, doesn't work, and you go to 6,000, it still doesn't work, understand that after you've hit 5,000, you're not getting the benefit of an increase in compression. The the FPC value is the average pre-stress in 2 directions. So if you average them out, you're typically in the 150, 175 range. But again, technically speaking, if you just start increasing the pre-compression in both directions, you will get a benefit. V sub P is always 0. Why? Well, it's a long story, but effectively I'll explain it the best I can. For the most part, I think all software that I'm aware of takes V sub P as 0. If you ever wanted to use V sub P, it would have to be done by hand, or there's got to be some kind of variable in the software. So why do we include it if it's always 0, or what actually is it? V sub P is effectively the vertical component of the strands at the column. So if you can look at the strands here, they're going to come up, curve down, and then when they hit the apex of this point, there's going to be a reaction of the tendons coming down directly into the column. So it's kind of like in the sense that if you have a column that continues up to another floor, the load of that column goes directly into the column below. It doesn't actually impact punching shear. So all of this force, that component, you can increase the capacity, or in the same way you can decrease the demand. The problem with the V sub P term is if the people in the field slightly change the point of inflection where this load comes from, then all of a sudden it's not going into the column core. You've missed it entirely, so you don't get that benefit. So it's highly dependent on obviously your design, but more dependent on how it is constructed. And if things move over 6, 8 inches a foot, from a structural standpoint, it's not going to make that big of a difference, but it's going to take away the V sub P term. So it's very hard to rely upon any benefit of that because it is so easily missed or changed. And I wouldn't rely upon that at all. Again, punching shear is our weak link. Don't screw around with punching shear. Take V sub P as 0. This is another example of how we would use V sub P. Now, if you look at this particular slide, the banded tendons are coming up through here and loading directly to that column. So you could make the argument in this direction, there's some component going right into the going right past the punching shear zone and right into the column. Okay, you can make that argument, but how do you make that argument for this strand over here? Are these strands way over there? They're nowhere near the column, so they have no benefit whatsoever. So in one direction, maybe, these 2 strands, maybe, but everything else, you can't argue. Now, what about in this direction? Again, you have the column reinforcement right there. These 3 strands and these 3 strands are now way outside the punching shear zone. So their point of inflection is going to push down into the slab, not into the column. So just because they push these out a little bit, which again doesn't change the flexural design, the balance load, the stresses. It has a huge impact on that V sub P term. So again, take it as zero, minimal benefits anyway, and you easily lose that benefit in the field. So that's why it's typically considered zero. For punching shear resistance, as I mentioned before, for light superimposed loads, I think stud rails work great. We use them for pretty much everything we do outside of landscaping, pools, or amenity decks, or podiums. They can be installed upside down. They keep the soffit flat. It interacts well with other reinforcements. I mean, I wish I had bought stock in them. They're a great product. We use them from band to anchorage reinforcements, and we use them all over the place. Obviously, column caps can be used for punching shear. And increases the cross-sectional area, increases the section modulus. Again, I would recommend for larger superimposed loads. Again, there's nothing wrong with stud rails and higher loads, but you start getting, the rails in thicker slabs. They have to be piggybacked because they don't make, rails 12 inches tall. All of a sudden, they're 3 inches on center spacing. They go out 5 feet or something from the column. It just looks like it's overextended. So for the higher loads, we use caps. The drop panel that you use in rebar concrete, you can use in PT. It does not apply. You don't have to use drop panels in a PT segment or segment. You can use whatever you want. If you're more used to the drop panels, great. Use those for punching shear if you would like to. In theory, you could use higher strength concrete, but if you're using the PT equations for punching shear, once you go past 5,000, it's not going to help you. So if you can use higher strength, look at using the rebar only equations. And this is what stud rails look like. I know we've seen a few photographs. Obviously, this is the column vertical rebar here. The stud rails come off the face of the column in each direction. They interact well with the rebar and post-tensioning. You can see there's barely any path of travel difference between the stud rails here and here, even though they are sandwiched by the reinforcement. These can be installed upside down. It's kind of like a number 4 bar with a 135 hook on each end. There's really no difference between the two systems. Again, they work really well with light superimposed loads in our opinion, and we use them all the time. The other nice thing about stud rails is that when you're doing structural observations, the rail should be the same cover as the rebar, as the same cover as the PT at the face of column. So when you look at the face of column, all 3 of those things should be in the exact same plane. If you are at a typical interior column and those 3 are not in the same plane, something is off. You don't need calipers or a tape measure. If those things are jumping or there's gaps between them, right off the bat, you can know something's wrong. So the stud rails themselves, since they are a manufactured product, they should be extremely accurate based on the slab thickness. That'll tell you at the column if the PT and rebar is located correctly. This is another great picture of a column cap. I'm a huge fan of column caps. Nothing makes me feel more secure about a building standing up than a big chunk of column cap holding up these podium slabs. This is what a podium slab looks like in the real world. I know it's very difficult to see, but the cap outline is right over here across this segment of zone. Hopefully you can see the vertical rebar of the columns. I realize it's very congested. Banded PT over the top, uniform direction PT. There's a lot of stuff in these podium slabs, but the cap does a lot of extra depth, which is obviously an extra D value for your bending stress, or bending strength. The depth of the section will increase P over the cross-sectional area will increase, and the S will increase. And the S increase is really what buys you a lot of forgiveness in post-tension designs. Now, the one thing about caps that is very different from drop panels is that you can use whatever you want. There's no minimum width or depth. You could literally use a 2-inch deep cap that's 1 inch off the face of the column, and technically you could use those section properties. I typically wouldn't recommend that. We don't use anything less than 4 foot square. And to be honest, we haven't used a 4 foot square cap in years just because the stud rails would replace those caps for lighter buildings. The drop panel requirements do not apply to post-tension slabs. That is a rebar only system. You can use a 5 foot square cap, an 8 foot square cap. You have the same abilities. Whatever you want to do, it's engineering judgment. But again, the L/6 requirements do not apply to PT slabs. As I mentioned before, the area of the cap will reduce the P over A value. So make sure that if you're really kissing 125 and you add a cap, you don't violate that section. The dimensions of the cap will increase your section modulus. So an S of a 12-inch slab versus the S of a 12-inch slab with a cap is substantially different. And when your S goes up or increases, the M over S stress goes down. That means technically you could reduce the amount of strands you have in your system and still satisfy stresses. So in that sense, caps are a lot more useful than just for punching shear strength. This is a punching shear failure of a PT slab in Northridge. And again, nothing funny about this particular slide, but this kind of highlights the dramatic nature of post-tensioning, of a punching shear type failure. Once it goes, there's no ductility, there's no, hysteretic behavior. It just slides right down the actual system. The column is still standing pretty, but there's nothing holding it up. One of the things that we do with post-tensioning that is a code requirement, and in my opinion, probably the most important code requirement that we have, are what are called integrity strands. This is again, prescriptive requirement per the code. And in each direction, you can see these two strands here and these strands right here. You need to have two strands each direction that are embedded inside the vertical column rebar. So basically what the intent is when you have some massive overload condition, whether it's vertical load or in this case seismic, and the concrete just turns to rubble, as you can see in this photograph, the tendons here, which are continuous from one side of the building to the other, are embedded in that column. So the column is going to prevent them from dropping. And basically this is going to act as a big safety net, catenary action, a big spider web, and just hold this thing together. Now, obviously this thing took a beating. It's going to get demoed, or it did get demoed and rebuilt, but it didn't come down. The continuous reinforcement embedded in those columns allowed for load distribution and just for the thing to hang on. The other thing about this photograph, which is telling, is that obviously the concrete has turned to rubble. It's now just rocks. The tendons are the only thing holding this building up because they're unbonded. They don't need the concrete. Look at all this rebar that was previously bonded to the concrete. As the concrete turned to rocks, there's no even remnants of concrete on those bars. Those bars are now useless. They're nothing more than something to hang your clothes off of. Since the tendons are unbonded and they don't need the concrete for strains, for stresses and stuff like that, the post-tensioning that's embedded in these columns is the only thing holding it up. So in that sense, the integrity strands for the past photograph is what held that structure up. So that's really very, very important. Now, if you look at this particular photograph, you have the column vertical rebar here. The bands go right through the column core, but note these two strands right here are not inside that column core. That is a code violation that needs to get fixed. So when I do structural observations, one of the things I look at very carefully is to make sure those two strands are inside the column core, obviously in both directions, but usually one in the smaller direction of the column is more problematic. But again, that is a code violation that needs to get fixed. This is another example of that situation. You can see the banded tendons going right through the column core, which is great, but these strands are here, not even close to the column, and these strands are way over there. They have to go through the interior of that column. Again, there's a lot of code sections that maybe don't make a lot of sense. This is the one that is extremely important. I strongly recommend that whoever's doing the observations key on this aspect to make sure it's taken care of. So things to look out for. For a good design, typically the pre-compression values are between 150 to 250 psi on the average. If you have localized higher areas, that's fine. But if you're in the 300 plus range on the average, I think your pre-compression is too high. You might want to look at your slab thickness. Way over 275, you're probably using way too much PT, or your slab is too thin. Now, technically, there's nothing wrong with over compressing a slab if that's your way to get a thin slab to work numerically. The problem is, there's just a lot of stuff in a thin slab at 275 psi or higher. Also, the more pre-compression you have, the more the slab is going to want to move, shrink, or shorten. The more the slab shortens, you have the potential for what's called restraint to shortening cracks, or RTS. RTS is probably the major cause of cracking in post-tension slabs. Not strength. This is a shrinkage issue, but it's one of those detailing issues that we'll deal with, in a different class. But the more load you put into a segment or an element, the more it moves, the more potential for cracking. So aside from just weigh, 5 pounds of stuff in a 3-pound bag, more pre-compression leads to more movement. Now, obviously, you can use larger pre-compression values to reduce the fluxural stresses to make a thin slab work, and I've seen a lot of engineers do that, but take some advice from an old man, try and avoid that design approach. Oppositely, if you're using stresses that or you're using a design that works with very, very low balance loads, everything is 50% balance, 60% balance, and you're satisfying stresses all over the place, that's a good indicator that your slab may be too thick. So unless you are having, a certain design philosophy where you're not trying to overbalance, if you're not trying to balance anywhere close to 100%, this is a quote-unquote normal design, but your balance loads are very low, but everything works, you might want to check your slab thickness. The rebar over the columns, if it is substantially more than the code minimums, the 00075 ACF equation, I would say check your slab because maybe it's too thin. In my experience, vast majority of the slab rebar over the columns is covered by the code minimum. And if you have, 50% of your columns has a lot more than the minimums, I'm guessing that you have a lot of pre-compression or overbalancing because your slab is too thin. Similar to pre-compression or high pre-compression forces, significant overbalancing can be a numerical way to make a thin slab work. Again, you're pushing up with some loading that from the calculation standpoint, subtracts from the dead and the live load. The problem with overbalancing is that when you stress concrete 3 days after you pour it, there's no ceilings, there's no partitions, there's no live load. It's just gray concrete. And so if you're cranking up with 300% balance loads and the vast majority of that load it's going to resist won't be there for 6 months, that's what leads to blowouts, to cracking, to over cambering. So again, it's a numerical solution to make a thin slab work, but it's going to cause you a tremendous amount of potential problems during construction. So please try to avoid that. One thing that we've noticed recently, especially in parking structures or retail, anything that has to do with parking, the amount of conduit is increasing exponentially for the EV, electrical vehicles, Wi-Fi, solar, stuff like that. Conduit right now, I would say in the last 5 years or so, has been our biggest problem. And again, our slabs are thinner than everybody else's, and trying to, just put a massive amount of conduit in slabs just doesn't work. So from the beginning, I would strongly recommend, notes on the drawings, talking to people, but don't be surprised when they have 150 pieces of conduit they want to put in your 7-inch deck, and that causes a whole bunch of obvious problems when those two things are trying to pour together. So with that, I thank you for your time. If you have any questions, you can email myself or Dirk through our email address or through Canvas. And again, thank you for listening, and talk to you later.